Okay, so you now know the space in which quantum field theory is going to happen, and that's Fock space. So we're going to want to start developing some tools for working in Fock space. And one very basic tool that we used a lot in quantum mechanics was called the completeness relation. So let's now, oh, let me change that. Um, Let's now ask ourselves, what is the completeness relation in box space? Okay. And remember what the completeness relation said in normal quantum mechanics? You had the identity operator was equal to, and then we basically had a sum over all of the states, and let's use momentum eigenstates. So this could be a sum over any complete basis. We've chosen the momentum eigenbasis. And this is the statement that you would have found in normal one-particle quantum mechanics. This would be a correct statement in the one-particle Hilbert space. It cannot be a correct statement in Fock space, though, because this whole operator lives in the one-particle Hilbert space. And you know that Fock space is a sum of a naught-particle Hilbert space, a one-particle Hilbert space, a two-particle Hilbert space, and so on. So let's start correcting this formula. We're obviously going to add some stuff to it. So the first thing that we could add is the identity operator acting in the no-particle Hilbert space. So that's just ket vacuum, bra vacuum. Plus, then we've got this term over here, which is the identity operator acting in the one-particle Hilbert space. Now let's add the term that corresponds to the identity operator acting in the two-particle Hilbert space. Okay, so what should we have? Well, again, we should have a complete sum over all of the states. Our states are labeled by two momenta, K1 and K2. So we need a sum over D3K1, D3K2. Then we will have ket K1, K2 and bra K1, K2. So this may have been your guess for what the piece of the identity in the two-particle Hilbert space would be. And that guess is almost correct. You're just off by a factor. The factor that you're off by sitting up front, we need a 1 over 2 factorial. And we're going to keep on building up this formula. But what I would like to do now is explain why is that 1 over 2 factorial needed. Okay, so let's see. To do that, well, we should be able to take this object with that 1 over 2 factorial normalization. So I'm just rewriting it over here. And this, we claim, should act like the identity operator in the two-particle Hilbert space. So let's take this and let's act on a state inside the two-particle Hilbert space. So there we go. We're going to act on that state. Okay, so what do we get? Well, we've got 1 over 2. We've got integral d3k1. We've got integral d3k2. Then we've got the ket k1, k2. And now we have to calculate an inner product. What inner product do we have to calculate? Between this bra and this ket. Now, you've seen that inner product before, so let's just write it down. There are two terms. First of all, K1 may be equal to P1 and K2 may be equal to P2. But if you remember, there was a second term that came about when K1 was equal to P2 and K2 was equal to P1. And remember what we said why we got these two terms. It was because of bosonic statistics. the ket P1, P2 is symmetric in P1 and P2. You can swap those and you've got the same state. So when you calculate this in a product, whatever formula you write down has to be symmetric under swapping P1 and P2, and that's why we needed the second term. Good. Okay, so now let's do the integrals. We can easily do the integrals because we've just got some delta functions sitting here. So we'll have 1/2, okay? And let's see what we get. From the first collection of delta functions, K1 is set equal to P1 and K2 is set equal to P2. So we get P1, P2. Good. From the second set of delta functions, now it's K1 that is set equal to P2. And it is K2 that is set equal to P1. But as we said before, because of bosonic statistics, these two states are identical. So I can add them to get 2 P1, P2, and the factor of 2 exactly cancels against the half. Okay, so let's just summarize what were the key things. So the value of the inner product over here, why did we get this double sum over here? That was due to bosonic statistics. And then when we added these two to get 2 P1, P2, that was again because of bosonic statistics. So that 1/2 factorial up front was needed purely because of bosonic statistics. So I hope it's clear why we need that 1/2 factorial. Now, why don't you try to write down what is the next term? The term in the 3-particle Hilbert space. And I'm just going to clear some space. So you write it down on your page, then we'll write it down together, and you can see if you got it right or not, which is the best way to tell whether you know what's going on. So what is the piece of the identity operator that lives in the 3-particle Hilbert space? That's the question you should be tackling. Okay, good. So there's going to be a coefficient. If you guess that coefficient is 1/3 factorial, well done. Spot on. That's correct. Then we've got an integral, d3k1, an integral, d3k2, an integral, d3k3. We need to integrate over all 3 of these momenta because the 3-particle state is labeled by those 3 momenta. And for the completeness relation, we want to sum over a complete set of states. So that would be the piece of the identity that lives in the 3-particle Hilbert space. And you just keep going. Okay, so you'd have plus, plus, and so it would continue. Just to be absolutely sure, let's write down the form in the n-particle Hilbert space. So we'd have a 1/n factorial, would have an integral, d3k1, then d3k2, d3k3, all the way up to d3kn. And the ket would be labeled with k1, k2, going all the way up to kn. And then the bra would be labeled by K1, K2, going all the way up to Kn. And this would be the piece of the identity operator that acts in the n-particle Hilbert space. And the sum of all of these terms together gives the identity operator acting on Fock space. So this is the completeness relation in Fock space.